Hello there, and welcome to the Sleepy Science Channel. Tonight, we are exploring one of science's greatest and most famous discoveries. Gravity is the force that holds you to Earth. It guides the moon through the sky and shapes the fate of every star in the universe. It is always present, yet rarely noticed. It keeps oceans from drifting into space. It bends light from distant galaxies. It even alters the passage of time. Gravity is not just the reason things fall. It is the hidden architect of the entire cosmos. It sculpts planets into spheres and gathers dust into blazing suns. It choreographs the motion of worlds, and it whispers through space-time in ripples born from colliding black holes. Every orbit, every tide, every sunrise exists because of it. And yet, it is one of the weakest and least understood forces we know of. Scientists still don't even know what it is, and this is one of the greatest mysteries in all of cosmology. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Let your shoulders soften and allow your breathing to slow. And as your mind begins to gently unwind, join me as we embark on this cosmic journey together. Let's begin. Gravity makes time run differently, causing your feet to age faster than your head. Gravity does more than guide motion through space. It also changes the pace at which time itself unfolds. Deeper in a gravitational field, time runs a little slower. Higher up, where the field is slightly weaker, time runs a little faster. That means the top of your head is aging ahead of your feet by an unimaginably small amount. The difference is tiny in daily life, yet it is real and measurable with precise clocks. This is not about feeling older. It is about the fabric of the universe keeping different rhythms at different heights. Gravity links space and time so tightly that you cannot change one without nudging the other. It turns now into something local, not universal. Over long spans, the effect adds up. Time becomes another landscape with slopes, and gravity is part of what shapes its contours. A black hole is gravity so intense that light cannot escape. There are places where gravity does not just bend paths. It closes the exit entirely. Around a black hole is a boundary called the event horizon. Cross it, and every possible future path leads deeper inward, even for a photon. That is why the horizon is not a solid surface. It is a line in space-time where escape becomes impossible. Outside, black holes can still reveal themselves. Nearby gas can whirl into a hot, bright disk that shines in X-rays. Stars can be stretched by tidal forces and torn apart into streams. At the center is not a giant vacuum cleaner. It is a compact object whose mass is packed into a region so small that space-time curves sharply. The most haunting part is that a black hole can be defined by only a few properties, yet it can influence everything around it with quiet authority. The moon stays in orbit because it is constantly missing Earth. The moon is not hovering. It is moving sideways so quickly that its continual fall never catches the planet. Gravity pulls it inward, while its sideways motion carries it forward. The balance creates a curved path that repeats month after month. If the moon suddenly stopped, it would not hang in place. It would drop toward Earth. If gravity vanished, it would not spiral outward. It would fly off in a straight line. Orbit is a perpetual compromise between inward fall and forward motion. This is why launches to space are not mainly about going up. They are about building the right sideways speed. It is also why orbits can be high, low, circular, or stretched into long ellipses. The Moon's path is a visible lesson in how gravity works at a distance, shaping motion without touch, and turning falling into a stable dance. Gravity sculpts planets into near spheres given enough time. Small objects can be lumpy because their own weight is not strong enough to rearrange them. Once a body grows large enough, its gravity begins to overpower the strength of rock and ice. High spots slump. Valleys fill. Over millions of years, the shape relaxes toward a sphere. This is why worlds like Earth look round from space, while many asteroids resemble jagged potatoes. The process is slow, but it is relentless. Gravity acts like a patient sculptor, pressing material toward the lowest energy form. Inside a young planet, heavy materials tend to sink, while lighter materials rise. That sorting can build layers, create dense cores, and power long-lived internal heat. A sphere is not perfection. Rotation can cause bulges, and impacts can leave scars. Still, the overall roundness is a signature that gravity has been quietly reshaping the body from within. Tides happen because gravity stretches oceans more than it pulls. If gravity pulled equally on every part of Earth, the ocean would simply follow along and nothing would slosh. Tides appear because the Moon's gravity is stronger on the side facing it and weaker on the far side. That difference in strength creates a stretching effect across the whole planet. Water, which flows easily, responds by forming two broad bulges. As Earth rotates through those bulges, coastlines experience rising and falling sea levels. The Sun also contributes, and its effect can reinforce or reduce the lunar pattern depending on alignment. Tides do not just move water. They transfer energy and can slowly change rotations and orbits over long periods. They also shape coastal ecosystems, carving intertidal zones that live between ocean and land. The next time you see a tide chart, you are looking at a map of gravity's gradient, translated into the rhythm of the sea. You weigh slightly less at the equator because Earth spins. Weight is the force you feel from the ground pushing up on you. At the equator, Earth's rotation is fastest. That spin creates an outward effect that slightly reduces how hard the ground must push to keep you moving in a circle with the planet. The change is small, yet it is measurable. It is one reason Earth is not a perfect sphere. The equator bulges outward because rotation counteracts gravity there more than it does near the poles. If Earth spun faster, the difference would grow. If it spun much faster still, rocks and oceans would struggle to stay put. This is a vivid reminder that gravity is not the only influence on what you feel. Motion matters too. Your weight depends on where you stand, how fast you are moving, and the shape of the world beneath your feet. Even down has a tiny regional accent. Gravitational waves are ripples in spacetime from colossal collisions. When massive objects accelerate, they can disturb spacetime itself, sending out traveling waves. These waves do not move through space, like water ripples on a pond. They are ripples of the space and time we inhabit. As one passes by, distances stretch in one direction and squeeze in another, then reverse, in a pattern that carries energy away from the source. The strongest events involve dense objects like black holes and neutron stars spiraling together. Long before the merger, the orbit shrinks as energy is radiated outward, and the frequency of the waves rises like a cosmic chirp. What arrives at Earth is incredibly faint, yet it carries a clean signature of the masses and the motion that created it. This gives astronomy a new sense beyond light. It is a way to learn about violent events even when dust, gas, or darkness hides them from telescopes. Without gravity, stars would never ignite. and atoms would remain isolated. In the early universe, matter was spread out and pooling. Gravity provided the slow gatherer. It pulled gas into denser regions, and those regions pulled in more gas, building clouds that could collapse. As a cloud contracts, it heats up. Eventually, the center can become hot and dense enough for atomic nuclei to collide and fuse, and a star is born. That same gathering process also helps atoms meet and stay together. Chemistry requires close encounters, repeated collisions, and stable environments. Gravity makes those environments by forming planets and by holding atmospheres and oceans in place. It turns a thin fog of particles into structured worlds where complexity can grow. Without it, the universe would be a far more lonely place. There would be no long-lived suns to power climates, no stable surfaces to build on, and no slow cosmic assembly line turning simple ingredients into rich, evolving systems. Newton linked a falling apple to the motion of the moon. He was not proving that fruit bonks reveal physics. He was connecting two scenes that seemed unrelated: a simple drop in an orchard and a bright disk sailing overhead. The daring step was to treat them as the same phenomenon, operating at different distances. That idea let him imagine a single rule that could explain why an apple accelerates downward and why the moon does not. Once that link was made, motion stopped being a collection of local quirks. It became a unified clockwork where the same law could steer projectiles, tides, and planets. The shocking part is how little data he had compared with modern science. The leap was conceptual. It invited the world to believe that nature is consistent across Earth and sky. That belief changed everything that followed. Einstein predicted gravity bends light, and eclipses confirmed it. Light seems weightless, so it feels impossible that it could be deflected. Yet if spacetime is curved, then even a beam of light follows that curvature. Einstein calculated how much starlight should shift as it passes near the sun. The problem was visibility. In normal daylight, you cannot see stars close to the sun's glare. A total solar eclipse solves that, because the moon blocks the bright disk and reveals nearby stars for a few minutes. In the early 20th century, expeditions photographed those star positions during an eclipse and compared them to the same stars seen at night. The measured shift matched the prediction closely enough to electrify the world. It was not only a new result. It was a new way to test deep ideas about reality, using the sky itself as a laboratory. The sun's gravity warps starlight into natural cosmic magnifiers. Gravity can act like a lens without glass because it bends the path of passing light. When a massive object sits between us and a distant source, it can focus that light toward Earth. The result can be a brighter, larger, or even duplicated image of something unimaginably far away. In perfect alignment, the light can form a ring, like a halo drawn by geometry. What makes this thrilling is that it gives astronomers a tool they did not build. Nature provides the telescope, and we supply the camera. These cosmic magnifiers can reveal galaxies too faint to see otherwise, and they can help map where mass is hiding, including mass we cannot see directly. Every time a background object brightens unexpectedly, it may be telling us that gravity has briefly turned the universe into an optical instrument. Mercury's orbit drifts in a way Newton could not explain. Mercury loops around the Sun in an ellipse, and that ellipse slowly rotates over time. Most of that rotation can be explained by the gravitational nudges of other planets. Yet a small leftover shift remains stubbornly unaccounted for. Astronomers checked for errors, then even proposed an unseen planet closer to the Sun. Nothing fit cleanly. The solution arrived when gravity itself was reimagined. Near the Sun, space-time curvature is stronger, and Mercury feels it more than any other planet. When Einstein applied his equations, the missing drift appeared naturally, with no extra planet required. It was a quiet kind of triumph. A tiny discrepancy became a doorway. It showed that even familiar orbits can carry hidden information, and that precision can reveal when a beautiful old theory needs a deeper replacement. Your phone's location works because gravity alters satellite time. GPS depends on timing so precise that a tiny error becomes a large mistake. Your phone figures out where it is by comparing when signals arrive from multiple satellites. That method only works if the satellite clocks stay synchronized with clocks on Earth. They do not, unless corrections are built in. Up high, gravity is weaker, and time runs a bit faster for the satellites. At the same time, the satellites are moving quickly, and motion makes time run a bit slower. Both effects matter, and the net difference would make GPS drift badly if ignored. The amazing part is that relativity is not a philosophical add-on here. It is infrastructure. Every map pin and every turn-by-turn instruction quietly relies on the universe keeping different rhythms at different altitudes. Your pocket device is doing astronomy-grade physics, over and over, without you noticing. Astronauts float because the station is always falling earthward. It looks like gravity has vanished up there, but it has not. The station is still deep in Earth's gravitational field. The difference is that everything inside is falling together. The station, the astronauts, their tools, and even the air are all sharing the same free fall path. With no solid floor pushing up on their bodies, they feel weightless. That feeling is not the absence of gravity. It is the absence of support forces. This is why spilled water forms drifting spheres and why an astronaut can hover with a fingertip push. The station is moving sideways fast enough that, as it falls, Earth curves away beneath it. The fall never ends, so neither does the float. It is a beautiful trick of motion. Gravity is the stage, and speed is what keeps the actors from hitting the ground. Astronauts grow taller in orbit as gravity stops compressing spines. On Earth, the spine is under constant load. The soft discs between vertebrae are slightly squeezed, and the curves of the back are shaped by that daily pressure. In orbit, that load disappears. The discs can rehydrate and expand a little, and the spine can lengthen. Astronauts often gain a small amount of height during a mission, and it can feel strange at first, like the body is subtly unfamiliar. This is not a superpower. It can come with back discomfort as muscles adjust to a new posture. It is also temporary. When astronauts return to Earth, gravity resumes its steady compression, and the spine settles back. What makes this fascinating is how quickly the body responds to changed conditions. Height is not fixed like a number on an ID card. It is a living measurement that depends on forces, fluids, and the quiet engineering of your own tissues. Gravity keeps Earth's atmosphere from slowly drifting into space. Air seems light, yet every molecule has mass, and every molecule is part of a restless swarm. At the top of the atmosphere, particles move fast and collide often. Some collisions fling a molecule upward with enough speed to escape, and over geological time that process can matter. Earth holds onto most of its gases because its gravity is strong enough, and because the planet is not too hot. Temperature matters because heat means speed. A very hot upper atmosphere leaks more easily. This is one reason small, warm worlds struggle to keep thick air, while larger worlds can hang on to lighter gases. Earth's retention has consequences everywhere. It allows clouds, weather, breathing, and the shielding layer that filters harsh radiation. When you inhale, you are taking part in a balancing act between random motion and gravitational grip, an ancient tug of war that has lasted for billions of years. Gravity holds oceans down, yet also shapes global sea level. Sea level is not simply the edge where water meets land. It is a surface defined by gravity and by Earth's rotation. Water naturally settles onto an invisible shape called an equipotential surface, meaning it spreads out until it cannot flow downhill any further. That surface is not smooth. It bulges, dips, and tilts because mass is unevenly distributed inside Earth and across its surface. Places with extra mass can pull water slightly toward them, raising local sea level. Places with less mass can do the opposite. Winds and currents add motion on top, yet gravity sets the baseline that the ocean constantly tries to return to. This is why the phrase global sea level hides complexity. The ocean is not in a perfect bowl. It is draped over a living planet with a lumpy gravitational field. Every coastline is measuring that field, day after day. Earth bulges at the equator, where spin partly resists gravity. Earth rotates, and rotation changes what it means to be held down. At the equator, the surface is moving fastest, and the required inward pull to keep you on a circular path is greatest. Gravity provides most of that inward pull, so the effective felt gravity is slightly reduced there. Over long spans, this matters for the shape of the planet itself. Rock is strong, yet it is not infinitely strong. Given enough time, the planet relaxes into a shape that balances gravity and rotation. The result is an oblate spheroid, wider around the middle than from pole to pole. This bulge affects everything from satellite paths to the calibration of maps. It is also a reminder that Earth is not a static object. It is a spinning body obeying physical rules, reshaping itself in response to forces that never switch off, even while life goes about its day. Mountains slightly weaken local gravity by increasing distance from Earth's center. Gravity depends on how far you are from the mass doing the attracting. Climb a mountain and you are a little farther from Earth's center, so the pull decreases. That decrease is tiny, yet instruments can detect it. What makes this surprising is that a mountain is also extra mass, and extra mass increases gravity. Two effects compete. Distance weakens, added rock strengthens. In many places, the distance effect wins, so the net gravity at a summit can be slightly lower than at sea level nearby. This turns mountains into natural experiments. By measuring these differences carefully, scientists can learn about the density of the crust beneath and about how mountains are supported by deeper structures. The story is not only about height, it is about hidden architecture. A peak can hint at what lies far below it, because gravity carries information through rock as faithfully as it carries you down a slope. Dense underground rock strengthens gravity, and satellites can detect it. If you could see mass the way you see light, Earth would look patchy and textured. Some regions contain denser rock, buried ridges, and thickened crust. Those concentrated masses pull more strongly, creating small bumps in the gravitational field. Satellites that pass overhead feel those bumps. They speed up slightly as they approach, then slow down as they move away. By tracking a satellite's motion with extreme precision, scientists can map gravity variations across the globe. The maps can reveal ancient mountain routes, buried volcanic provinces, and the scars of old collisions that reshaped continents long before humans arrived. This is not guesswork. It is a kind of remote sensing that can see through clouds, forests, and even darkness, because gravity does not care about weather. It only cares about mass. That makes it a powerful way to read Earth's deep history without digging. Satellites track groundwater by watching tiny shifts in gravity. Water has weight, and when huge amounts of it move, gravity responds. In dry seasons, groundwater can be pumped away and the mass beneath a region decreases. In wet seasons, aquifers refill and mass increases again. Satellites designed to measure gravity changes can detect these slow pulses. They do not see individual wells or pipes. They see the combined effect, as if the land itself is breathing in water and breathing it out. This has become a remarkable tool for understanding drought, farming pressure, and long-term changes in water storage. It can reveal depletion in places where, on the ground, measurements are sparse, and it can show recovery where conservation efforts are working. The fascination here is scale. Gravity can turn an invisible resource into a measurable signal from space. It reminds us that the planet is not only shaped by rocks and plates, it is also shaped by the movement of water, quietly rearranging mass beneath our feet. Gravity mapping reveals buried basins and ancient impact scars. Some of the most dramatic features on Earth are hidden. Sediment can fill old craters. Forests can cover ring-shaped mountains. Ice can bury entire landscapes. Gravity offers a way to sense these structures without seeing them directly. An impact scar often has a distinctive pattern. Rock may be fractured and less dense in the center, while denser material may be uplifted around it. A buried basin can show up as a gravity low if it is filled with lighter sediments. By combining gravity maps with other clues, scientists can identify candidates for ancient impacts and reconstruct chapters of Earth's past that erosion berates, as erased at the surface. This kind of detective work is thrilling because it uses a force you feel every moment as a probe into deep time. The ground under your shoes holds stories older than any museum. Gravity helps translate those stories into shapes we can recognize, even when the visible evidence is gone. The Moon contributes to Earth's gravity through moving ocean mass. When the Moon reshapes the ocean, it is not only raising and lowering shorelines, it is also moving a vast amount of water across the planet. Water is mass, and mass affects gravity. As tidal bulges travel, the distribution of weight on Earth changes, and that slightly changes the gravitational field. Sensitive instruments can detect these minute variations. They matter for precision studies of Earth's rotation and for careful satellite tracking, because satellites respond to the field they fly through. This is a beautiful loop. The Moon's gravity moves the ocean. The moved ocean changes Earth's gravity. That shifting gravity then influences motion in space above the waves. It is a reminder that the planet is interconnected in ways that feel almost too subtle to be real. Yet, they are real. The sea is not only water and wind. It is also a moving part of Earth's gravitational fingerprint, reshaped by a neighbor hanging in the sky. Falling is universal, but weight depends on what supports you. Mass is how much matter you have. Weight is how strongly you are being supported against a gravitational field. That difference can feel abstract until you change the situation. Stand on a scale and the spring inside is being compressed by the upward force the scale exerts on you. Step into an elevator that accelerates upward and the scale reading increases because you need a bigger support force to match the motion. In a fast downward acceleration, the reading drops because the support force is reduced. In free fall, it can approach zero, even though gravity has not switched off. This is why astronauts can feel weightless while still being pulled toward Earth. The key is contact. Weight is a conversation between you and whatever is holding you up. It is not a fixed property stamped onto your body. Once you notice that, everyday sensations become clues. Your stomach lurch in an elevator is physics speaking through your nervous system. On Mars, you could jump higher because gravity pulls less strongly. Mars has less mass than Earth, so its gravity is weaker at the surface. That means the same push from your legs would launch you higher and keep you in the air longer. Your body would still feel heavy in some ways, yet movement would have a different rhythm. Steps would stretch out. Falls would last longer, giving you more time to react. Sports would change instantly. A simple hop could become a floating arc, and a throw could travel farther for the same effort. Yet Mars would not feel like the Moon. You would still have enough gravity to keep a clear sense of down and to make things drop reliably. The fascination is that gravity rewrites choreography. It changes what muscles must do, and it changes how you time your motions. Mars is not only a world of red dust and thin air. It is a world with a different physical beat, where familiar actions would feel slightly dreamlike, as if the planet is giving you extra hang time to think. On Jupiter, you would weigh far more if solid ground existed. Jupiter's gravity at the level of its cloud tops is stronger than Earth's, so your body would feel heavier. Simple movements would demand more effort. Standing up would be a workout. Breathing could feel harder because your chest muscles would have more weight to lift and lower. Yet the real twist is that Jupiter does not offer a firm surface to stand on. It is mostly hydrogen and helium, turning into denser and stranger states as you go deeper. If you descended, pressure would rise, winds would howl, and the environment would become utterly hostile long before anything like ground appeared. So the idea of weighing yourself there is both vivid and impossible, which makes it such a powerful thought experiment. Jupiter teaches two lessons at once. Gravity can be stronger, and a world can still be unwalkable. It reminds us that planet does not always mean a place with land beneath your feet. A neutron star squeezes a sun's mass into a city-sized sphere. When a massive star ends its life, its core can collapse so violently that electrons and protons are forced together into neutrons. The result is a neutron star, only tens of kilometers across, yet containing more mass than our Sun. That compression is so extreme that ordinary matter is pushed beyond familiar states. The surface gravity becomes mind-bending, and the star's magnetic field can be ferocious. Many neutron stars spin rapidly, and some sweep beams of radiation through space like lighthouse lamps. When those beams cross Earth, we detect pulses that arrive with astonishing regularity. This is why they are called pulsars. The wonder is that a single object can be both tiny on a cosmic map and enormously influential. It can warp space-time, accelerate particles, and serve as a precision clock all at once. Neutron stars are what happens when gravity pushes matter to the edge of what physics can comfortably describe. Near a neutron star, a pebble would hit like a freight train. The gravitational pull near a neutron star is so strong that falling objects gain incredible speed in a very short distance. Even a small drop becomes a violent plunge. The energy of impact comes from motion, and motion comes from gravity converting potential energy into kinetic energy. Near such a dense star, that conversion is extreme. A modest pebble, harmless in your hand on Earth, would strike with devastating force. This is not because the pebble becomes magical. It is because the environment gives it an immense acceleration. The same strength also creates powerful tidal effects. The difference in gravity between your near side and far side would be enormous, pulling unevenly on anything extended. It is a place where the word down becomes a trap, and where ordinary intuition fails quickly. Thinking about this is a reminder that gravity is not a single experience. It has a range. What feels steady on Earth can become overwhelming elsewhere. Neutron stars are gravity turned up to a level that makes small things behave like weapons. Gravity weakens rapidly with distance, faster than intuition suggests. If you double your distance from a mass, its gravitational pull does not have. It drops to a quarter. That steep fade is why a small object can feel dominant up close, yet irrelevant from far away. It is also why space is not a place where gravity turns off. Astronauts in orbit are still close enough to Earth to be strongly influenced. The real change is how little the pull there is across their bodies, and how fast they are moving sideways. This rapid weakening also shapes the architecture of solar systems. A planet rules its neighborhood nearby, but the sun still governs the overall dance. Far beyond the planets, even the sun's grip becomes a faint suggestion, and passing stars can tug comets onto new paths. Gravity reaches everywhere, yet its strength is a story of distance, and distance is a ruthless editor. Gravity pulls comets back, even after centuries in deep space. Some comets spend most of their lives in darkness, far beyond the familiar planets. They drift for hundreds of years, sometimes far longer, before returning to the inner solar system like old visitors who remember the way. Their return is not guided by any engine. It is the slow, persistent influence of the sun, shaping a long, oval path through space. When a comet swings inward, sunlight wakes it up. Ice begins to turn to gas, and dust is released, building a glowing head and an elegant tail. Then the comet swings back outward again, fading into cold silence. The orbit is like a promise kept over generations. People can be born, live entire lives, and never see that same comet again. Yet the solar system remembers. Gravity keeps the schedule, even when the timetable is longer than a human story. Jupiter's gravity herds asteroids into stable Trojan groups. Jupiter does not only dominate with size, it also creates pockets of stability where smaller bodies can gather and linger. Along Jupiter's orbit are two special regions where the combined gravitational influence of Jupiter and the Sun, together with the motion of the asteroid, allows a long-lasting balance. Asteroids trapped there are called Trojans, and they travel in two swarms, one leading Jupiter and one trailing behind. It is as if the giant planet has companions marching with it, held in formation by mathematics. These asteroids are not neatly arranged like soldiers. They bob and weave within their regions, yet the overall pattern persists. Studying them is like reading an archive from the early solar system. Many may be leftovers from planet formation, preserved because they found a safe gravitational shelter. Jupiter's presence can be a threat, but it can also be a refuge. Saturn's rings exist where gravity tears moons apart. Saturn's rings look delicate, but their origin is tied to destructive forces. Close to a giant planet, tidal gravity can become so strong that a moon cannot hold itself together. Instead of remaining a single body, it can be pulled into fragments that spread into a disk. Those fragments collide, grind, and sort themselves into countless pieces that orbit Saturn in a flat plane. Over time, the ring system becomes a shimmering record of motion, made of ice and rock in constant circulation. Each particle follows its own orbit, yet the whole structure behaves like a living surface, with waves, gaps, and sharp edges shaped by nearby moons. The beauty comes from a balance. Saturn's gravity is strong enough to organize the rings, yet it is also the reason a larger moon could be torn into them in the first place. Creation and destruction share the same cause. Roche limits mark where structures fail under tidal gravity. There is a boundary around a planet where being whole becomes difficult. Cross it, and tidal forces can overwhelm the strength holding an object together. The Roche limit is not a cliff you fall off. It is a threshold that depends on density, structure, and what the object is made of. A loose, rubble-like moon can be disrupted farther out than a solid, coherent one. Inside this region, the planet's gravity pulls harder on the near side than the far side, stretching the object. If the material cannot resist, it fractures. This idea explains why some planets have rings and why moons tend to orbit outside certain distances. It also helps scientists interpret what might happen during close encounters in space. A passing comet that ventures too near a massive world can be pulled into a chain of fragments, each continuing on its own path. The Roche limit turns gravity into a sculptor with a breaking point, and the results can be spectacular. Earth's gravity causes the moon to slowly drift away. Earth and moon are connected by tides, and tides are not perfectly efficient. As Earth rotates, ocean bulges do not line up exactly with the moon. They are carried slightly ahead by the spinning planet. That offset bulge tugs on the moon, giving it a small push forward in its orbit. A forward push raises the orbit, so the moon gradually moves farther away. The exchange is subtle yet steady over immense time. It is a reminder that orbits are not frozen. They can evolve through the slow transfer of energy and angular momentum. This recession also leaves traces in geology. Ancient growth patterns in fossils and layered sediments can preserve clues about past day lengths and tidal rhythms. The moon's outward drift is not a dramatic escape. It is a long, patient migration measured in millimeters per year, driven by the everyday motion of water and the steady turning of Earth. The moon's gravity slows Earth's spin, lengthening days. The same tidal interaction that nudges the moon outward also acts like a brake on Earth's rotation. Tides create friction. Water moves across the seafloor, currents stir, and energy is dissipated as heat. That lost energy comes from Earth's spin, so the planet's rotation very gradually slows. The result is that days become longer over geological time. This is not something you notice in a lifetime, yet it is part of Earth's deep history. Long ago, the planet spun faster, and the rhythm of sunlight across landscapes was different. As rotation slows, the timing of atmospheric circulation and ocean patterns can shift, and life adapts within those changing cycles. The most captivating part is the partnership. A distant companion in the sky can influence the length of your day through nothing more than gravity and friction. The moon does not need to touch Earth to shape timekeeping on a planetary scale. It simply needs to orbit and to raise tides. Gravity can capture wanderers, turning passing objects into moons. Most flybys in space are brief. An object approaches, it curves around a planet, and it departs again. For a true capture, energy must be removed from the visitor's motion. Sometimes that happens through a three-body interaction, where the object passes near a planet that already has a moon, or travels through a swarm of debris. The gravitational choreography can shuffle energy between participants, leaving one body bound to the planet, while another carries away the excess. In other cases, a pass through an atmosphere can slow an object enough to be trapped, though that is a harsh route that can also destroy it. Captured moons often have unusual orbits. They may travel backward relative to the planet's spin, or tilt far from the equatorial plane. These odd paths are like fingerprints of a dramatic arrival. Each captured moon tells a story of near misses and lucky losses, where gravity turns a fleeting encounter into a permanent relationship. Venus spins strangely, nudged by gravity over immense time. Venus rotates slowly and in the opposite direction to most planets. It is a world where the sun would rise in the west if you stood on its surface. The reasons behind this odd rotation are still studied, and gravity plays a role in the long-term evolution. Tidal interactions between Venus and the Sun can apply torques that influence spin state, especially over vast spans. The planet's dense atmosphere also matters, because moving air can push on the surface and exchange angular momentum. Over time, these influences can steer rotation towards stable configurations, even if the path there involves chaos and reversals. Venus reminds us that a planet's spin is not merely an accident of birth. It can be shaped, reshaped, and redirected. Gravity is part of that story, working with tides and torques like a slow hand on a dial. When you look at Venus as an evening star, you are seeing a world that keeps time in a very different way. Small gravitational nudges can make orbits chaotic over millions of years. The solar system looks orderly, yet it is filled with tiny exchanges. Every planet tugs on every other planet. Most of the time, these pulls average out, and the system remains stable. Over very long times, however, small effects can accumulate in ways that become unpredictable in detail. This is chaos in the mathematical sense. It does not mean immediate disaster. It means that extremely small uncertainties in starting conditions can grow until precise long-term forecasting becomes impossible. An orbit can shift from one pattern of influence to another, like a boat drifting between currents. Resonances can come and go, and a planet's eccentricity can slowly vary. What makes this so fascinating is the contrast. The same gravity that creates elegant repeating orbits can also seed complexity that no clockwork can fully tame. The solar system is both a poem of regularity and a laboratory of sensitive dependence, and both come from the same force. Gravity is the weakest force, yet it dominates the cosmos. On the scale of atoms, gravity is almost irrelevant. Electromagnetism holds your body together, binds chemistry, and shapes materials. Yet gravity has a special advantage. It always attracts, and it adds up. Positive and negative charges can cancel, but mass does not have an opposite that neutralizes it. So while gravity is individually feeble, it becomes overwhelming when you gather enough matter. That is why it rules the behavior of planets, stars, and galaxies. It shapes the collapse of gas clouds, the motion of stellar systems, and the structure of the universe on its largest scales. This dominance is not loud. It is patient. It works over long times and vast distances. Gravity is the quiet accountant of the cosmos, continuously summing every bit of mass and writing the final totals into motion. The weakest force becomes the grand organizer because the universe contains so much matter, and because gravity never stops adding. Galaxies form as gravity gathers matter into rotating star cities. In the early universe, matter was not perfectly smooth. Slightly denser regions pulled in more material, and that growth fed on itself. As gas collected, it began to cool and collapse, fragmenting into places where stars could form. Meanwhile, angular momentum shaped the overall structure, encouraging the growing system to rotate. Rotation helps spread material into disks, where spiral patterns can emerge like long-lived waves. In a spiral galaxy, billions of stars share a common gravitational home, along with gas, dust, and unseen mass that deepens the gravitational well. The result is a star city on a cosmic scale, with neighborhoods of newborn stars and quiet suburbs of ancient ones. Gravity provides the glue, but it also provides the story arc. It gathers, it compresses, and it keeps the system bound for billions of years. When you look at the Milky Way on a clear night, you are seeing the luminous trace of that gathering stretched across the sky like a river of suns. Galaxy clusters are bound by gravity across millions of light-years. A galaxy is already immense, yet galaxies themselves assemble into larger families. In a cluster, hundreds or thousands of galaxies orbit a shared center of mass. The space between them is not empty. It can contain a vast reservoir of very hot gas, and the entire cluster is embedded in an even larger gravitational structure that helps hold it together. Inside a cluster, galaxies can be distorted by close passes, their shapes stretched, their gas stripped, and their star formation altered. Clusters are also signposts of the universe's growth. They form where matter has had time to collect on the largest scales. Their gravity is strong enough to influence light from objects behind them, and their hot gas can shine in X-rays, revealing the cluster's invisible architecture. Thinking about a cluster is like zooming out from a city to a continent. Gravity still does the organizing, but now the map spans millions of light years, and the timescales are almost beyond imagination. Dark matter is inferred because gravity exceeds visible mass. When astronomers measure how fast stars orbit within galaxies, they find a puzzle. The outer regions move too quickly to be held by the gravity of visible stars and gas alone. The same mismatch appears when looking at galaxy clusters. Something unseen seems to deepen the gravitational wells. This invisible component is called dark matter, not because it is gloomy, but because it does not emit or absorb light in the usual way. Its presence is inferred through motion and through gravitational effects on large structures. Dark matter is not a single confirmed substance yet, but the evidence for extra mass is strong across many observations. This turns gravity into a messenger. It tells us there is more to the universe than the luminous parts. It also means that what you see in a telescope is only a fraction of what is there. The galaxies are like lanterns hung on a much larger scaffold. Gravity lets us feel the scaffold even when we cannot see it, and that mystery is one of modern science's most compelling invitations. Gravity traps hot gas between galaxies, creating glowing halos. In large galaxy groups and clusters, gravity can hold onto gas that would otherwise drift away. This gas is heated to extreme temperatures as it falls inward and collides, and at those temperatures it shines in X-rays. These glowing halos are not decorative. They are massive reservoirs that carry a significant fraction of the ordinary matter in the system. They also act like a weather system on a cosmic scale. Galaxies moving through the hot gas can have their own gas stripped, which can shut down star formation by removing the raw material for new stars. Meanwhile, cooling regions can feed material back towards central galaxies, sometimes fueling energetic activity around supermassive black holes. The halo is like an atmosphere for the cluster itself, held together by gravity and lit by heat. It turns the space between galaxies into something tangible, dynamic, and influential. When you imagine a cluster, do not picture only scattered galaxies. Picture a vast, hot sea of gas, invisible to our eyes but bright to X-ray instruments, shaped and contained by gravity. The cosmic web exists because gravity pulls matter into filaments. On the very largest scales, the universe is not random. Matter is arranged in a web-like pattern, with long filaments connecting dense nodes and huge voids in between. This structure grew from tiny early irregularities that gravity amplified over time. Regions slightly denser than average drew in more matter, and as they grew, they pulled from their surroundings along preferred directions. The result is a network where galaxies tend to form along filaments and gather at intersections, where the gravitational wells are deepest. This is not a web made of threads you could touch. It is a map of where mass has collected under gravity's long influence. The cosmic web also guides the flow of gas that feeds galaxies, and it shapes where clusters form. When you look at images of deep space, you see points of light. The web is the hidden structure connecting them, a skeleton of gravity written across billions of light years. Gravity makes collapsing stars spin faster, like skaters pulling arms in. When a star's core contracts, its rotation can speed up dramatically. This comes from conservation of angular momentum. If you bring mass closer to the axis of rotation, the spin rate rises. The same principle lets a figure skater speed up by pulling in their arms. In a star, The effect can transform a slow rotation into a rapid one as the core shrinks from a vast volume to something much smaller. This acceleration can influence everything that happens next. It can shape magnetic fields, channel explosions, and determine the spin of the compact remnant left behind. Rapid rotation can also help create jets that pierce through surrounding material, carrying energy far from the core. The beauty of this idea is its simplicity. A familiar motion on an ice rink becomes a key to understanding stellar death and rebirth. Gravity does the squeezing, and rotation responds. In that response, the star's final moments can become more dramatic, more asymmetric, and more powerful. Supernova remnants form new systems because gravity endures. A supernova can look like pure destruction, a star torn open in a blazing outburst. Yet after the light fades, gravity remains, still shaping the debris. The expanding cloud carries heavy elements forged in the star and in the explosion itself. As that cloud plows through surrounding space, it can compress nearby gas, creating dense regions that begin to collapse. Over time, those collapsing regions can become new stars, and around them, new planetary systems can assemble. In that way, gravity turns an ending into a beginning. The remnant itself can also become a strange object, like a neutron star, that continues to influence its environment with strong gravity and intense T, radiation. The story has a long timescale. An explosion lasts days to months, but its aftermath can shape millions of years of star formation. Gravity is the thread that ties these chapters together. It is the force that gathers material before the star is born, holds the star while it shines, and then reclaims the scattered pieces afterward, so the universe can build again. Gravity ignites fusion by crushing hydrogen until it heats. A star begins as a cold cloud that is too diffuse to shine. As gravity gathers the gas, it falls inward and speeds up. Collisions become more frequent, and the material heats as it is compressed. Eventually, the core becomes dense and hot enough for hydrogen nuclei to overcome their mutual repulsion in rare but vital events. When fusion starts, it releases energy, and that energy pushes outward. A star then becomes a balance between inward gravitational squeeze and outward pressure from hot gas and radiation. This balance is what lets a star shine steadily for billions of years. The ignition is not a spark like a match. It is a threshold reached through relentless compression, a slow climb toward conditions where nuclear reactions can proceed. Gravity provides the climb. Without it, gas would remain a wandering mist. With it, the universe can light up, turning invisible clouds into suns that sculpt planets, power climates, and make night skies worth staring into. Brown dwarfs fail as stars because gravity falls just short. Between planets and stars lies a curious middle class. Brown dwarfs form the way stars do, from collapsing gas. They can become hot enough to glow, and some can fuse a limited form of nuclear fuel early on. Yet they do not reach the sustained hydrogen fusion that defines a true star. Their mass is not quite enough for gravity to compress the core to the required temperatures and pressures, so they shine mostly from leftover heat, slowly cooling and dimming over time. They are sometimes called failed stars, though that is unfair. They are successful in their own strange category, bridging two kinds of objects. Brown dwarfs can have weather, clouds, and even companions orbiting them. They are faint, which makes them hard to find, yet they may be common. Their existence is a lesson in thresholds. A little more mass and gravity would tip them into stardom. A little less and they would be more planet-like. Gravity sets the dividing line, and brown dwarfs live right on it. The Sun's gravity sets every planet's orbital speed. Close to the Sun, planets race. Farther out, they drift more slowly, and the reason is simple and profound. A tighter orbit requires a higher sideways speed to keep from falling inward too quickly. Mercury must move fast to keep curving around the Sun instead of plunging toward it. Neptune can move more slowly because it is already far away, and the inward pull is weaker there. This relationship turns the solar system into a kind of speed map. Distance becomes a dial that sets tempo. It also explains why inner years are short and outer years are long, even though every planet is following the same basic rule. The Sun is not dragging planets along. It is shaping the path they naturally trace, and speed is the price of staying in that path. When you picture planets orbiting, you are really picturing a negotiation between falling and racing sideways. Earth and Moon orbit a shared center, hidden within Earth. It feels natural to say the Moon orbits Earth. In a deeper sense, both bodies orbit a shared balance point called the barycenter. This point lies along the line between them, and it sits inside Earth but not at Earth's center. Earth, therefore, performs a subtle wobble as the Moon goes around, like a dancer leaning into a partner's spin. This is not a poetic detail. It affects the way we model Earth's motion, and it matters for precision tracking of spacecraft and satellites. It also helps explain why eclipses and tides align with orbital cycles that feel wonderfully clock-like. The shared orbit is a reminder that gravity is mutual. Earth pulls on the Moon, and the Moon pulls on Earth with equal strength. The difference is response. Earth is massive, so it moves less, if it still moves. Even the ground beneath you participates in a slow celestial waltz. The Sun wobbles because planets tug it, and that reveals exoplanets. A star with planets is not a still lamp at the center of a system. It is part of the dance. As planets orbit, they tug on their star, and the star shifts slightly back and forth. From far away, that wobble can be detected as tiny changes in the star's velocity along our line of sight. The star's light shifts minutely toward red and blue as it moves, in a pattern that repeats with the planet's period. This method has revealed worlds that never pass in front of their stars, including massive planets that are easier to detect because they tug harder. It is a thrilling kind of inference. You do not see the planet directly. You watch the star flinch, as if an unseen companion is pulling on its sleeve. Each wobble is a gravitational whisper saying, something is here. Something is orbiting, and it has mass. Binary stars let scientists measure mass through gravitational motion. When two stars orbit each other, gravity turns them into a laboratory you can watch from across space. By measuring how long the orbit takes and how large it is, astronomers can determine the combined mass of the pair. If they can also measure how much each star moves, they can separate the masses too. This matters because mass is the trait that controls a star's entire life story. It sets brightness, lifetime, and the kind of ending a star will have. Binary systems therefore become calibration points for stellar physics. Some binaries eclipse, letting us learn sizes and densities with unusual clarity. Others reveal themselves through shifting spectral lines, like music that changes pitch as the stars move. In a sense, gravity is drawing a signature that we can read. The orbit is the handwriting. From that handwriting, we learn what the stars are made of and how they will change, even though we can never touch them. Spacecraft gain speed using gravity instead of fuel. A spacecraft can steal a little momentum from a moving planet, and it can do it without firing an engine. The trick is to approach the planet so that the craft swings behind it in the planet's direction of travel. Gravity then bends the craft's path, and the timing of that bend lets the craft leave with a higher speed relative to the Sun. The fuel savings can be enormous, which is why many deep space missions rely on this technique. It is not free energy. The planet loses a tiny bit of orbital energy in return, though the change is far too small to notice. What makes this feel magical is that speed becomes something you can borrow from motion already in progress. Space travel stops being only about carrying propellant. It becomes about choreography, about arriving at the right place at the right time, so gravity can do the heavy work for you. Gravity assists redirect spacecraft like cosmic billiards. Sometimes the most important gift from a flyby is not speed, but direction. A planet can bend a spacecraft's trajectory dramatically, turning its path like a cue ball glancing off a cushion. Engineers use this to aim probes toward targets that would otherwise be unreachable. One pass can tilt the orbital plane, shift the timing of future encounters, or send a craft inward toward the Sun, or outward toward the outer giants. The art lies in choosing the approach angle and the altitude. Too close, and the craft risks radiation or atmosphere. Too far, and the bend is too small. Each assist is a sculpted curve through space, planned years in advance and executed in hours. It is thrilling because it feels like using the solar system as a machine. The planets become moving tools. With the right geometry, gravity becomes a steering wheel, and the spacecraft's journey becomes a sequence of carefully chosen turns across a vast, silent table. Lagrange points balance gravity and motion in stable harmony. In the tug-of-war between two large bodies, there are a few special locations where the combined gravitational pulls and the motion of an orbiting object can balance. At these Lagrange points, a small spacecraft can stay in a fixed arrangement relative to the two larger bodies, with only modest corrections. Some of these points are stable, meaning objects can drift around them, like marbles in a shallow bowl. Others are unstable, meaning careful station keeping is required. Either way, they are real places in space, defined by gravity and geometry rather than by hardware. They can collect dust and small asteroids naturally, and they offer useful vantage points for exploration. What makes them so captivating is that they are not tied to a surface. They are invisible coordinates where physics allows a kind of hovering. Lagrange points reveal that gravity is not only a pull toward masses, it also creates structured pockets of balance, like calm eddies in a cosmic current. Space telescopes linger near Lagrange points for gentle stability. A space telescope wants darkness, steady temperatures, and a clear view. Certain Lagrange point orbits provide exactly that. Near the Earth-Sun system's second Lagrange point, a telescope can keep Earth and the Sun on roughly the same side, which helps with shielding and power. With the bright sources clustered together, a sun shield can block their heat and light, allowing sensitive instruments to cool and remain stable. Stability matters because tiny thermal changes can distort a telescope's shape, and that can blur observations. From this region, a spacecraft can also communicate reliably with Earth and scan the sky with fewer interruptions. It is not a perfect still point, so the telescope follows a looping path that stays near the balance region. The idea is elegant. Instead of forcing a telescope to fight its environment, mission designers place it where gravity and motion naturally reduce disturbances. The telescope becomes calmer, and in that calm, it can see farther. Gravity creates orbital resonances that lock moons into rhythm. When two orbiting bodies have periods that form a simple ratio, their gravitational tugs can repeat in a regular pattern. That repetition can build up over time, like a gentle push given at the same point in every swing. The result is an orbital resonance. Some resonances stabilize systems, keeping bodies in predictable spacing. Others can pump up eccentricity, stretching an orbit into a more elongated shape. Resonances can also explain why some moons line up in repeating sequences, and why gaps appear in rings where orbits would be unstable. This is gravity, acting like a metronome. It does not need to be strong in each moment, because the timing does the work. A small influence, applied repeatedly in phase, becomes significant. The wonder is that the solar system contains hidden musical relationships, and those relationships have consequences. Orbits are not only curves. They are rhythms, and gravity is the composer that rewards simple ratios with long-lasting patterns. Io erupts endlessly because Jupiter's gravity needs its interior. Io is a moon that should have cooled long ago, yet it is the most volcanically active world we know. The reason is not internal radioactivity alone. It is tidal flexing. As Io travels on its slightly eccentric orbit, Jupiter's pull changes enough to stretch and squeeze the moon over and over. That mechanical flexing turns into heat inside the rock, like bending a paperclip until it warms. The heating is continuous, so Io's interior stays restless. Lava lakes, towering plumes, and rapidly changing surfaces are the visible result. This is gravity doing work. It is converting orbital energy into internal heat through friction in the moon's body. The moon becomes a furnace powered from the outside. What makes Io so astonishing is the scale of the effect. A world can be kept molten not by sunlight and not by its own birth heat, but by the repeated tug of a giant neighbor. Jupiter does not touch Io, yet it makes Io blaze. Tidal heating can melt worlds far from any star. Warmth does not always come from sunshine. A moon can be heated by being flexed, and that flexing can persist for billions of years if the orbit stays slightly non-circular. Each pass near its planet changes the gravitational pull just enough to deform the moon. Rock and ice resist deformation, and that resistance becomes heat. This mechanism can keep internal oceans liquid under thick ice, even in the cold outer solar system. It can also drive cryovolcanoes that erupt water and ice instead of lava. Tidal heating expands our sense of where active worlds can exist. It means that a moon can have energy, chemistry, and movement without being near a star's habitable zone. The energy source is orbital. It is steady, mechanical, and surprisingly durable. The idea is almost unsettling. A world can hide warmth in darkness, and the warmth can be supplied by gravity itself, working like a slow piston. In the search for life, that possibility changes the map. Europa may hide oceans kept warm by gravity. Europa's surface is bright ice, and it is traced with cracks that look like frozen motion. Beneath that shell, many lines of evidence point to a global ocean. If so, the question becomes, why is it not frozen solid? One leading answer is tidal flexing from Jupiter, which can generate heat within Europa's interior and keep water liquid. The ice shell may rise and fall slightly, and the resulting friction can warm the layers below. A subsurface ocean would be shielded from radiation and warmed from within, creating a stable environment where chemistry could unfold for long periods. The fascination is not only biological, it is geological. An ocean under ice would behave differently from Earth's oceans, and it could create currents, ice rafting, and shifting surfaces driven from below. Europa would then be a world with a hidden sea, a place where gravity and orbit may maintain liquid water in near darkness. That is a haunting thought and a compelling reason to explore. Enceladus erupts icy plumes as Saturn flexes its core. Enceladus is small, yet it sprays jets of water vapor and ice grains into space. Those plumes emerge from fractures near its south pole, and they feed Saturn's broad E-ring. For such a small moon, this activity is startling. The leading explanation is tidal heating. Saturn's gravity, together with orbital interactions, flexes Enceladus enough to generate internal heat. That heat can keep pockets of liquid water beneath the ice, and it can pressurize channels that vent material outward. The plumes are not only dramatic to watch, they are scientifically priceless. They place material from the interior into space, where a passing spacecraft can sample it without drilling through kilometers of ice. In a sense, Enceladus is offering clues voluntarily. Gravity supplies the energy, and the moon's fractures provide a path to the surface. It is a small world behaving like a geyser, driven by a giant planet's distant pull. Gravity can tear comets apart during close planetary passes. Comets are often fragile, built from ice, dust, and loosely bound rubble. When one passes close to a massive planet, the difference in gravity across its body can become extreme. The near side is pulled harder than the far side, and the comet is stretched. If its internal strength is low, it can split, and sometimes it can break into many pieces that follow one another like beads on a string. This is not an explosion from within. It is a failure under stress, caused by an uneven tug. The aftermath can be spectacular. Fragmented comets can create multiple tails, multiple glowing heads, and a complex set of future trajectories. Some fragments may be flung into new orbits. Others may be sent inward toward the Sun. Close passes, therefore, act like gravitational stress tests. They reveal what a comet is made of by how it breaks. They also remind us that the solar system is a place of encounters. A single flyby can transform a quiet traveler into a swarm of new objects, all because gravity varies across space. A planet's gravity determines whether hydrogen can linger. Hydrogen is the lightest element, and light gases are the easiest to lose. Whether a planet can keep hydrogen depends on how strongly it holds onto fast-moving molecules and how much heating the upper atmosphere receives. A massive planet with strong gravity can retain hydrogen more easily, which is one reason gas giants remain rich in it. Smaller rocky planets tend to lose hydrogen early, especially if they are warm or heavily exposed to intense young starlight. Losing hydrogen can change everything. It can strip away a primordial envelope, leaving behind a smaller world with a thinner atmosphere, and it can influence how water and other compounds evolve. This is why gravity is part of a planet's identity. It helps decide whether a world becomes a mini Neptune with a puffy envelope or a dense terrestrial planet with a rocky surface. Hydrogen retention is like a fingerprint of formation and survival. Gravity sets the grip, and the star sets the furnace. The outcome shapes what kind of planet you get. Gravity sorts atmospheres, letting heavy gases sink lower. In still air, gravity encourages denser gases to settle and lighter gases to rise. This is why, in a quiet column of atmosphere, pressure drops with height and the mix can vary. In practice, turbulence and wind stir the lower atmosphere, and that stirring keeps many gases well mixed up to a certain altitude. Above that region, where mixing weakens, gases can begin to separate more by molecular weight. This is not a simple layering like oil and water, but the tendency is real. Gravity also sets the scale height, which is how quickly air thins with altitude. A world with stronger gravity squeezes its atmosphere into a tighter layer, while weaker gravity allows a more extended envelope for the same temperature. That affects everything from how high clouds can form to how spacecraft experience drag. Atmospheric sorting is therefore a quiet partnership between gravity and motion. Stirring tries to mix. Gravity tries to stratify. The balance shapes the skies of every world. Escape velocity defines the speed needed to leave forever. To escape a world, you must climb out of its gravitational well without falling back. Escape velocity is the threshold speed that makes that possible, assuming you keep climbing and do not run into too much drag. It does not mean you instantly vanish. It means that, in principle, you can keep coasting outward and never be pulled back to the surface. The concept gives you a feel for how deep a planet's gravity well is. On a small body, a modest push can be enough to drift away. On a large planet, the required speed becomes enormous, which makes rocketry demanding and makes it harder for gases to leak into space. Escape velocity also helps explain why impacts can eject material from some worlds but not others. A powerful collision on a small moon can fling debris into orbit or into space. The same collision on a massive world may keep almost everything bound. Escape velocity is a simple number with wide consequences, a kind of gravitational gatekeeper. Earth's gravity retains gases for billions of years. Earth sits in a sweet spot. Its gravity is strong enough to hold on to key gases, yet not so strong that it kept a thick hydrogen envelope like a mini gas giant. Over time, this allowed a long-lived atmosphere that could evolve through volcanoes, chemistry, and life itself. Retaining gases is not only about the pull downward. It is also about the planet's temperature and the energy arriving from the sun. A hotter upper atmosphere gives molecules more speed, which makes escape easier. Earth's conditions have helped keep nitrogen and oxygen abundant, and they have helped keep water stable at the surface. That stability matters for erosion, climate, and the long cycling of carbon through rocks and oceans. This is one reason gravity belongs in the story of habitability. It sets the baseline for whether an atmosphere can persist through the storms of time, through impacts, and through the bright tantrums of a young star. Earth has had a long chance to become complex, and gravity has helped protect that chance. The Moon lost its air because gravity was too weak. The Moon may once have had a more substantial atmosphere, supplied by volcanic outgassing and impacts. Over time, that air did not last. With weaker gravity, gases escape more easily, especially when sunlight and energetic particles heat the upper layers. The Moon also lacks a thick protective atmosphere and a strong global magnetic shield, so the solar wind can directly interact with surface materials and, with any care, thin exosphere that forms. Instead of holding onto a stable blanket of air, the Moon ends up with a whisper-thin presence made of atoms that come and go. Some are knocked free by micrometeorite strikes. Some are released by sunlight hitting the surface. Many quickly escape into space or get captured again by the regolith. This makes the Moon a world of exposure. It has no weather in the usual sense, no long-lived clouds, and no pressure that allows liquid water to persist. The lesson is straightforward and profound. Gravity is part of what makes air possible, and without enough of it, the sky cannot stay. Pluto's atmosphere comes and goes with gravity and seasons. Pluto is small and cold, yet it can carry an atmosphere when conditions are right. The key is frozen nitrogen and other ices on its surface. As Pluto moves along its long orbit, sunlight changes enough to warm certain regions. When that happens, surface ice can sublimate into gas, creating a temporary atmosphere. As Pluto cools again, that gas can refreeze and collapse back onto the surface. Gravity plays a crucial role because it is just strong enough to hold some of that gas for a time, but not strong enough to make the atmosphere robust against loss and collapse. The result is a world with a sky that behaves more like a seasonal breath than a permanent cloak. This is a fascinating idea. an atmosphere does not have to be steady to matter. Even a thin, temporary one can shape surface frost patterns, move particles, and influence temperature across the globe. Pluto shows that gravity and sunlight can team up to create a sky that appears, fades, and returns on a timescale that feels almost like a slow heartbeat in the outer dark. Gravity drives rivers, dunes, and deltas downhill. Landscapes look still, but they are always on the move. Water slides downhill because gravity gives every drop a preferred direction. It starts as tiny trickles that join into streams, then into rivers that carve valleys and carry grains of rock like a slow conveyor belt. Wind-driven sand obeys the same rule. Each grain lifts and hops, then falls back under gravity, and that repeated settling builds dunes that migrate across deserts. When a river finally reaches calmer water, its speed drops and the load begins to settle. Sand, silt, and clay spread out and build a delta that can grow outward like a living hand. All of it is motion, guided by one simple bias. Downhill is never merely a concept. It is gravity writing paths into stone, and it is gravity sorting Earth's surface into channels, ridges, and fans over time. Waterfalls exist because gravity constantly seeks lower ground. A waterfall is a river discovering a sudden drop. Often the drop forms where hard rock resists erosion, while softer rock beneath is worn away. The hard layer becomes a ledge, the river spills over, and gravity accelerates the water into a plunge. That fall is not only dramatic to watch, it is an engine of change. The impact can excavate a pool, and swirling stones can drill the rock like a natural tool. Spray keeps nearby surfaces wet, which can speed weathering and widen cracks. Over long periods, the waterfall can migrate upstream as the cliff face erodes and collapses, leaving a gorge behind it. What you see is a moment in a slow retreat. Gravity supplies the energy and the river supplies the persistence. A waterfall is therefore a snapshot of geology in motion, a place where the landscape reveals how powerfully downward motion can sculpt the world. Gravity powers hydroelectric dams across the world. A dam stores water at height, and height is stored energy. When water is held behind a wall, gravity is waiting with patience. Open a path through turbines, and that waiting becomes motion, then electricity. The water rushes downward, spins blades, and turns generators that push electrons through wires. The elegance is that nothing needs to burn. The energy comes from a change in position. Rain and snow lift water into mountains through the broader cycle of evaporation and weather. Then gravity returns it to lower ground through rivers and reservoirs. Hydropower is therefore a partnership between sky and stone. It can respond quickly to demand, but it also depends on seasons and careful stewardship of ecosystems. Each time a light turns on from hydropower, it is gravity doing work at a distance, translated through engineering into a steady, usable flow of energy. Your inner ear senses gravity to define up and down. Inside your head are tiny structures filled with fluid and lined with delicate sensors. Two of them, called the otolith organs, contain crystals that shift with gravity. When you tilt your head, those crystals press on hair like cells, and the cells send signals that help your brain decide which way is down. Alongside them are semicircular canals that detect rotation, so turning your head produces a different pattern of fluid motion. Together, these systems help you balance, stabilize your gaze, and walk without constant calculation. They also explain why spinning can make you dizzy. The fluid keeps moving briefly after you stop, so your senses disagree about whether you are still turning. Gravity is therefore not only an external force. It is a reference your nervous system uses moment by moment. When you stand up in the dark and still know which way is upright, you are feeling gravity through biology. Plant roots grow downward by sensing gravity's direction. A seed does not need a map to find the soil beneath it. Roots are guided by a process called gravitropism. In root cells are dense particles that settle downward under gravity, and that settling triggers chemical signals. Those signals redistribute growth hormones so that cells on one side elongate differently than cells on the other. The result is a bend that aims the root into the ground. Shoots often respond in the opposite direction, growing upward toward light, while still using gravity as part of their guidance. This is not a simple on-off switch. Roots can adjust when obstacles are encountered, and they can integrate moisture, nutrients, and touch. Yet gravity provides the first dependable cue. It tells the plant where stability and water are likely to be found. It is remarkable to think that a silent force shapes forests before leaves ever appear. Long before a tree reaches skyward, gravity has already instructed it to anchor itself. In space, fluids drift upward without gravity's pull. On Earth, warm fluid tends to rise because gravity makes dense fluid sink and less dense fluid float. That process is buoyancy, and it drives familiar convection in air and water. In orbit, buoyancy nearly disappears because everything is in free fall together. Warm fluid does not reliably rise, and cold fluid does not reliably sink. Instead, surface tension and tiny pushes can dominate. Water can cling to surfaces in rounded blobs. Bubbles may refuse to separate from liquid. Even breathing becomes different because exhaled air does not automatically lift away from your face. Engineers and astronauts must design fans, vents, and systems that actively move fluids where gravity would normally do it for free. The fascination is how quickly ordinary intuition fails. A cup does not pour the same way. A damp towel does not drip. In microgravity, fluids reveal hidden rules that are usually masked by weight, and that makes spaceflight a constant lesson in the physics of everyday substances. Low gravity weakens bones because they bear less load. Bones stay strong by being challenged. When you walk, jump, or even stand, tiny stresses travel through your skeleton. Cells called osteoblasts and osteoclasts constantly rebuild bone, and they use mechanical strain as part of the signal for where to add or remove material. In low gravity, that strain is reduced. Over time, bone can lose density, especially in regions that normally carry weight, like hips and legs. Muscles can shrink for the same reason. They are not asked to work as hard, so the body economizes. This is why astronauts exercise intensely in orbit, using resistance devices that imitate weight-bearing forces. It is also why long missions demand careful monitoring and recovery plans back on Earth. The point is not that space is unhealthy by default. The point is that your body is tuned to gravity, and it uses gravity like a training partner. Change the partner, and biology changes its design. Microgravity reveals strange flame behavior without buoyancy. A candle flame on Earth stretches upward because hot gases rise. Buoyancy pulls fresh oxygen in from below, and it carries soot and heat upward in a teardrop shape. In microgravity, that rising flow largely vanishes, so flames behave in unfamiliar ways. They can become more spherical, and they can burn cooler and cleaner. Soot production can change, and the flame can appear dimmer and more blue. Without buoyant flow, combustion depends more on diffusion, meaning oxygen and fuel must mix by molecular wandering rather than by strong circulating debris. Currents. This matters for spacecraft safety. Fire does not spread the same way, and smoke does not drift upward toward a ceiling. Detection and ventilation must be designed with that in mind. It also matters for science. Studying flames in microgravity helps researchers understand combustion at a fundamental level, which can improve engines and reduce pollution. In a strange way, removing gravity makes fire easier to understand. Cooking changes without gravity because convection disappears. Many cooking methods rely on convection, which is driven by buoyancy. In a pot of soup, hot liquid rises and cooler liquid sinks, stirring the pot even if you do not. In an oven, warm air circulates and helps heat food from all sides. In microgravity, those natural currents weaken, so heat can pool in place and mixing becomes harder. Bubbles in boiling water can also behave oddly. They may cling and merge instead of rising away, which can change how efficiently heat is carried. Crumbs and droplets can float, which matters for electronics and air filters. Space kitchens therefore favor sealed packaging, controlled heaters, and fans that move air on purpose. The fascination is that gravity is part of flavor and texture. It affects how a batter settles, how steam escapes, and how heat travels through a meal. When you stir a sauce at home, you are not only mixing ingredients, you are collaborating with gravity and convection, two invisible helpers that are absent in orbit. Your voice shifts slightly as gravity alters airflow. Speech is a dance between breath, vocal cords, and the shape of your throat and mouth. Gravity influences the dance in small ways. On Earth, posture affects how your diaphragm and chest muscles manage air pressure. The position of soft tissues in the throat can change subtly when you lie down, which can alter resonance and make a voice sound different. Even the way mucus and moisture distribute in your airway is shaped by gravity, and that can affect clarity. In microgravity, fluids shift toward the upper body, and astronauts often experience a puffy face and a congested sensation. That can change how the vocal tract feels and how it vibrates. The change is not dramatic like a different person speaking, but it is noticeable. This is a reminder that your voice is not only a sound. It is a physical event inside a body that is always responding to forces. Gravity becomes part of your instrument, setting conditions for airflow and vibration every time you speak. Sports on the moon would feel slow and floating. On the moon, gravity is much weaker than on Earth, so every jump lasts longer. A basketball arc would hang in the air, and a sprint would feel like bounding through thick air, even though there is no air at all. The same push from your legs would send you higher, and landing would be easier on joints because the impact force is lower. Yet motion would also be trickier. With less weight, it is harder to generate friction for quick changes of direction. A hard shove could send you sliding farther than expected, and a fall could turn into a long tumble. Throwing would change too. A ball would travel farther for the same effort, and judging distance would require new instincts. Athletics would become a new kind of choreography, with longer airtime and different balance. What makes this captivating is how quickly your sense of what is possible would change. Gravity is a rulebook you rarely notice. Change it, and every sport becomes a new game. Cavendish weighed Earth by measuring gravity between small masses. In the late 18th century, Henry Cavendish used an experiment that looks almost delicate. He suspended a rod with small lead spheres at each end on a thin fiber. Nearby, he placed larger lead spheres. Gravity caused a tiny twist as the small masses were attracted toward the large ones. By measuring the twist and knowing the geometry, Cavendish could estimate the strength of gravity between known masses. From that, scientists could infer Earth's mass, since Earth's surface gravity was already measurable. The achievement was not about machinery. It was about patience, isolation from vibrations, and careful measurement of a force that is extremely weak but human scales. The experiment showed that gravity is universal and quantifiable, even in a room. It also helped pin down the gravitational constant, one of the most important numbers in physics. It is astonishing that the weight of an entire planet can be approached through a whisper of talk on a wire. Plumb lines point inward, shaping early maps and cities. A plumb line is one of the simplest tools ever invented. Tie a weight to a string, and gravity draws it toward the local direction of down. That direction defines vertical, which defines level surfaces, which defines building. Long before satellites, surveyors used plumb lines to establish straight walls, stable towers, and reliable canals. Entire cities were laid out with reference to this quiet truth. Down is not an opinion. It is set by the gravitational field where you stand. Over distances, that field points toward Earth's center, so vertical changes slightly from place to place. Early engineers learned to work within that curved reality, even if they did not describe it in modern terms. When you see an old cathedral that still stands true, you are seeing gravity used as a measuring device. The line does not need a compass or a clock. It needs only mass and patience, and it returns a direction that has guided human construction for thousands of years. The geoid shows Earth's true gravity shape, and it is lumpy. Earth is not a perfect sphere, and its gravity is not uniform. The geoid is a model of the surface where gravity and rotation balance, so that the ocean would rest there if it could flow freely without winds or currents. Because mass is distributed unevenly inside Earth, this surface rises and falls relative to a smooth reference shape. Dense regions pull more strongly and lift the geoid. Less dense regions allow it to dip. The result is a lumpy gravity map that looks almost like a misshapen potato when exaggerated for visualization. This matters for navigation, engineering, and understanding Earth's interior. It tells us where mass is concentrated, and it provides a more accurate definition of sea level for measuring heights. The geoid is also a reminder that gravity carries information. It is not just a force you feel. It is a field that encodes the hidden structure of the planet. When satellites map the geoid, they are effectively reading Earth's internal arrangement from space. Sea level follows gravity, not a perfect sphere. It is tempting to imagine sea level as a smooth shell around Earth. In reality, the ocean's surface is shaped by gravity, rotation, and the distribution of mass. Where gravity is slightly stronger, water is pulled into a higher surface. Where gravity is slightly weaker, the surface sits lower. Ocean currents and winds can pile water up temporarily, but the long-term baseline is set by the gravitational field. This is why precise sea level measurements require careful reference models. It is also why two coastlines at the same height above a simple sphere may not match the same physical sea surface. For satellite altimeters and for studying climate-driven sea level rise, this distinction is crucial. A change in ocean height is meaningful only when you know what surface it is measured against. The fascination here is that the ocean is an enormous instrument. Its surface is constantly adjusting, always trying to find balance within a lumpy gravitational landscape. Every calm horizon is tracing gravity's shape across the planet. Mountains can deflect plumb lines, surprising early surveyors. A plumb line points toward the local direction of gravity, and a mountain is extra mass. That extra mass can pull sideways, just a little, changing where the line points. Early surveyors sometimes noticed that careful measurements did not match expectations, even when their tools were good and their methods were careful. The explanation was not a mistake in the string. It was the mountain tugging. This effect is tiny, but it is real, and it became an early clue that gravity could be measured as a field with local variations. It also showed that Earth's mass is not distributed like a simple uniform ball. Mountains have roots, and different rock types have different densities. All of that affects the gravitational pull. The idea that a peak can bend a measuring line is wonderfully humbling. It turns a familiar landscape into an active participant in geometry. A mountain is not only scenery, it is a source of gravity, and it can quietly influence the direction you call straight down. Earthquakes subtly change gravity by shifting internal mass. An earthquake moves more than ground you can see. It can shift huge slabs of crust and alter the distribution of mass inside Earth. When mass moves, gravity changes slightly. These changes are far too small for your body to feel, but instruments and satellites can detect them in some cases. The pattern can reveal where rock compressed, where it expanded, and how the fault slipped during the event. It is like reading an invisible before and after image of the planet's interior. In the aftermath, Earth can continue to adjust through slow processes that follow the main rupture. Those adjustments can also leave gravitational signatures. This is fascinating because it gives earthquakes another dimension. They are not only shaking, they are rebalancing. They are reshaping the planet's mass distribution in ways that can be measured from orbit. Gravity becomes a diagnostic tool, adding a new layer to how we study hazards and how we understand the mechanics of the crust. Volcanoes alter gravity, hinting at magma movement below. Before an eruption, magma can rise and pool underground, and magma has mass. When large volumes shift position, local gravity can change slightly. Instruments on the ground can measure these changes, and when combined with other monitoring methods, they can help scientists infer what is happening beneath the surface. A rising magma body might increase gravity if dense material moves closer. An expanding chamber might decrease it if rock is cracked and replaced by less dense material. The interpretation is not always simple, but the signal can add valuable context. What makes this compelling is that gravity becomes a kind of stethoscope for the Earth. You cannot see the magma, yet the gravitational field responds to it. The volcano is not only building pressure, it is rearranging mass in the dark, and that rearrangement can be detected by careful measurement. Gravity, therefore, helps turn a hidden process into a readable one, which can improve understanding and, in some settings, help with forecasting risks. Melting ice sheets change gravity, and satellites watch it happen. Ice is heavy, and a continent-sized ice sheet is an enormous mass. When it melts, that mass is redistributed into the ocean, and the gravitational field changes. Satellites that measure gravity variations over time can detect these shifts, effectively weighing ice loss from space. This approach does not rely on cloud-free images or on a single glacier's surface appearance. It measures mass change directly, which makes it powerful for tracking long-term trends. The consequences are not only global sea level rise. Local sea level patterns can change because ice itself exerts gravitational pull on nearby ocean water. As ice mass shrinks, its pull weakens and water can redistribute. The result can be counterintuitive changes in regional sea level. What is striking is the scale of observation. A satellite can sense a change in Earth's gravity caused by melting ice thousands of kilometers away and translate it into a record of how the planet is changing. Gravity becomes a global monitor, revealing shifts in the distribution of water across Earth. Gravity gradiometers can reveal underground voids without digging. Gravity itself is subtle, but its rate of change across distance can be even more revealing. A gravity gradiometer measures how the gravitational field differs from one point to another nearby. If there is a hidden void, a tunnel, or a low-density cavity beneath you, the local field changes in a distinctive way. The device can detect those gradients, and help map what lies below the surface. This technique has applications in geology, mineral exploration, and in locating features that are otherwise hard to see. It is not a magic X-ray that shows perfect pictures. It is a sensitive measurement that must be interpreted carefully and often combined with other data. Still, the idea is thrilling. You can learn about empty space in rock by sensing how strongly the planet pulls on you. It turns gravity into a probing signal, a way to detect absence as well as presence. When you walk over ground, you usually think of it as solid and known. A gradiometer reminds you that the subsurface can be full of surprises, and gravity is one way to find them. The kilogram was once defined through gravity and balance. For a long time, how much is a kilogram was tied to what balances could compare here on Earth. A scale does not measure mass directly. It measures the support force needed to hold something up against a gravitational field. That is why careful metrology had to think about local gravity, air buoyancy, and even tiny variations in altitude. Two identical objects can seem to weigh slightly differently if the gravitational field differs. This made high-precision measurements surprisingly Earth-dependent. Over time, scientists worked to escape that dependence, because a unit of mass should not wobble with geography. The story is a reminder that everyday measuring tools are really gravity translators. They turn a deep cosmic interaction into a number on a dial. When you picture a kilogram in your mind, you're picturing a human agreement that once leaned on the planet's pull to make it practical. Freefall feels weightless, even though gravity remains. The strange feeling of weightlessness is not the same as the absence of gravity. It is what happens when every part of you accelerates together. On the ground, the floor pushes up on your feet, and that upward push compresses your body. Your nerves interpret that compression as weight. In free fall, there is no floor force. Your organs, bones, and skin are all moving along the same path, so nothing inside you is being pressed. A drop tower experiment makes this vivid. For a brief moment, objects inside the falling capsule float, as if gravity has vanished. Then the capsule stops, and weight returns instantly as contact forces come back. This difference between gravity and support is one of the most clarifying ideas in physics, because it explains why astronauts can float, why roller coasters can lift your stomach, and why the sensation of weight is really the sensation of being held up. Orbit is continuous falling combined with sideways speed. An orbit is a fall that never finishes. Imagine throwing a stone across a field. Gravity curves its path downward until it hits the ground. Now imagine throwing it so fast that, as it falls, the surface curves away beneath it. It keeps missing the ground. That is the heart of orbit. The spacecraft is always being pulled inward, yet its sideways motion keeps carrying it forward. Different sideways speeds create different shapes. Slow sideways speed produces a steep, low arc. Higher sideways speed produces a longer, higher path. Add more speed, and the path can stretch into a very elongated oval. This is why rockets spend so much effort building horizontal velocity, not just altitude. It is also why orbits feel elegant. They are not held up by anything. They are pure motion under gravity, a balance between inward curvature and forward momentum that can persist for years in the quiet of space. A heavier object does not fall faster in a vacuum. If you remove air, falling becomes wonderfully fair. A feather and a hammer accelerate together because gravity gives the same acceleration to all masses. The difference we see in daily life comes from air drag, which acts more strongly on objects with large surface area compared to their weight. In a vacuum chamber, that advantage disappears. The result is surprisingly emotional to watch, because it contradicts a deeply held instinct. It also reveals something profound about nature. Gravity does not care how massive you are when it sets your rate of fall, because the same mass that increases gravitational pull also increases inertia in exactly the right way. The two effects cancel in the acceleration. This is not a coincidence. It is a clue about how gravity fits into the structure of physics. When you see two very different objects landing together, you are seeing a principle that guided Einstein toward his deepest ideas, and you are seeing why falling power can be a universal experience. Air resistance causes the difference, not gravity playing favorites. Air is not empty. It is a sea of molecules that pushes back on anything moving through it. That push depends on shape, speed, and how much turbulence is created. A crumpled paper ball falls faster than a flat sheet because it slips through the air with less drag. A skydiver accelerates, then reaches terminal velocity when drag grows large enough to balance their weight. At that point, the fall becomes steady, not because gravity is weaker, but because the opposing force has caught up. This turns a fall into a negotiation. Gravity pulls, air pushes, and the result is the motion you see. It is also why parachutes work so well. They do not change gravity. They change drag. The beauty here is that you can feel the physics with your hand out a car window. The air becomes solid enough to lean on. Falling is not only about gravity. It is about the medium you fall through. Gravity sets the maximum height of mountains before rock collapses. A mountain is a stack of rock, and rock has strength, but it also has limits. As a mountain grows, the pressure at its base increases. Eventually, the lower layers can begin to deform, flow, or fracture under their own weight. That sets a practical ceiling on how tall mountains can become on a given world. On a planet with stronger surface gravity, the same rock would fail at a lower height, so landscapes would tend to be smoother and more subdued. On a world with weaker gravity, the same rock could stand taller, and jagged relief could persist for longer. This is why topography can hint at planetary conditions. Gravity is not only shaping orbits, it is shaping scenery. It decides whether a peak can remain proud or whether it must slump and spread. When you look at a high mountain, you are seeing a temporary victory of structure over weight, a balance that is always being tested by the planet's steady pull. Stronger gravity would flatten landscapes because structures fail sooner. Imagine walking on a world where every object feels heavier and every step costs more effort. Over time, that same extra weight would press on cliffs, ridges, and tall formations, pushing them toward collapse. Landslides would be more common, slopes would reach stability at gentler angles, and the maximum height of dramatic features would shrink. Rivers would likely cut differently too, because heavier water exerts stronger forces on the ground it flows over. Even the way trees grow would change, because trunks and branches must support their own mass. The whole planet would feel more compressed. This is a powerful way to understand that gravity is part of design, not only of motion. It determines what kinds of structures can exist, from mountains to organisms. It also suggests why some worlds might look surprisingly smooth from orbit. They may have had their sharp edges edited away by simple weight. Gravity becomes a sculptor that prefers low profiles because high profiles become fragile. Weak gravity lets small bodies stay jagged, like many asteroids. Small worlds often look like they were carved with a rough chisel. Many asteroids have sharp edges, steep walls, and irregular shapes because their gravity is too weak to pull them into roundness. Rock that would slump on a larger planet can stand at odd angles on a tiny body. Even loose debris can cling in place if there is little pull to rearrange it. This gives asteroids an almost handmade appearance, as if they are relics from an unfinished workshop. The jaggedness is also a clue about history. A small body can be shattered by impacts and reassembled into an awkward shape, and weak gravity cannot easily smooth the result. Landings on such bodies are therefore unusual. A gentle push can send dust drifting for minutes, and the horizon can change abruptly because the object is not spherical. Weak gravity turns a world into a place where geometry feels unfamiliar. Up and down still exist, but the landscape keeps its scars, and its silhouette stays stubbornly irregular. Some asteroids are rubble piles, held together by gentle self-gravity. Not every asteroid is a solid boulder. Some are more like a loosely bound heap of rocks and dust that clump together after collisions. Their own gravity is enough to keep the pieces from drifting apart, but not enough to crush the gaps between them. This makes them surprisingly fragile. A close encounter with a planet can reshape them, and a spacecraft impact can excavate material in ways that reveal how loosely the interior is packed. These bodies can also spin only so fast. If rotation increases beyond a limit, the weak gravitational cohesion cannot hold the rubble together, and material can slide or even escape. Rubble piles are fascinating because they act like time capsules of violence. They are built from fragments, yet they persist for millions of years as coherent objects. When you imagine landing on one, picture a surface that might behave like gravel with a sky above it. In such weak gravity, a small hop can lift you. The asteroid is holding itself together by a force that is real, but very soft. Gravity can compress planets enough to create metallic hydrogen deep inside giants. In a gas giant, there is no single moment where sky becomes ground. Instead, pressure rises steadily as you go deeper, because gravity stacks layer upon layer of gas above you. Eventually, the pressure becomes so intense that matter behaves in ways that feel impossible at the surface. Hydrogen, normally a gas made of tiny molecules, can be squeezed into a state where electrons move freely, like they do in metals. This metallic hydrogen is thought to conduct electricity extremely well. That matters because moving conducted material can help generate powerful magnetic fields. The deeper you go, the stranger the physics becomes. Temperature and pressure reach levels that turn familiar substances into exotic phases. The wonder is that gravity is the engine behind it all. It is not chemistry alone. It is the weight of an entire planet pressing inward, transforming simple elements into unfamiliar forms. When you look at Jupiter or Saturn, you are seeing a planet whose most extraordinary materials are hidden far below, created by compression that never rests. Gravity drives planetary cores to form because heavy elements sink. When a young planet is hot and partially molten, its materials can move and sort themselves. Dense metals like iron tend to sink, while lighter silicates rise. Gravity provides the direction and the motivation. Over time, this separation builds a core and a mantle, like a cosmic version of sediment settling in a jar. The core is not a small detail. It can control a planet's magnetic behavior, its internal heat flow, and the way it responds to impacts. As the core forms, gravitational energy is released as heat, adding to the planet's internal warmth. That heat can fuel volcanism and tectonics for long periods. Core formation is therefore an early chapter that echoes across billions of years. It is also a reminder that planets are not just lumps of material. They are structured bodies with layered interiors, and those layers are often the result of gravity sorting the ingredients by density. In a sense, gravity turns chaos into architecture, building hidden hearts inside worlds. The sun's gravity makes light lose energy as it climbs outward. Light can be shifted by gravity in a way that feels almost like fatigue. When a photon climbs out of a deep gravitational region, it ends up with less energy than it started with. That energy change shows up as a redshift, meaning the light's wavelength becomes longer. This is not because the photon gets older or rubs against anything. It is because energy and time behave differently in different gravitational conditions. The effect is small near the Sun compared to more extreme objects, but it is real and it is measurable. It is also conceptually beautiful because it ties gravity to the color of light. Gravity becomes part of what a spectrum means. When astronomers read starlight, they are not only learning about temperature and composition, they are also reading the imprint of gravitational environment. Light carries not just information from where it was emitted, but also a record of what it had to climb through to reach us. In that sense, every photon is a traveler returning from a place where time runs on a slightly different rhythm. The Shapiro delay shows light takes longer passing near massive bodies. Space is not a simple, empty stage. Near a massive object, spacetime is shaped in a way that affects travel times. One striking test is the Shapiro delay. When a radio signal passes near the Sun on its way between Earth and a spacecraft or another planet, it arrives a little later than it would if space were flat. The signal is still traveling at the speed of light locally, yet the geometry it moves through is different, and the effective path in spacetime becomes longer. This delay has been measured with remarkable precision using radar and radio tracking. It is a subtle effect that becomes a powerful confirmation of relativity, because it is hard to explain with older ideas of gravity. The fascination is that you can detect curved spacetime with timing. You do not need a telescope image. You need patience and a clock, and then you can watch the universe reveal that distance is not only about meters. It is also about the shape of spacetime between 2 points. Gravity can trap photons in unstable orbits around black holes. There is a region around a black hole where light can, in theory, circle the hole, not because it wants to, but because spacetime curvature is just right. This region is sometimes called the photon sphere. The orbit is not stable like a planet's. A tiny disturbance sends the photon either plunging inward or escaping outward. Yet the idea matters because it helps explain the dramatic silhouettes seen in black hole imaging. Light that passes near this region can loop around, creating bright rings and complex paths before it either escapes or is captured. It is like a hall of mirrors built from gravity alone. The photon sphere also reminds us that orbit is not reserved for massive objects. In curved spacetime, even light can be guided into looping routes. The instability adds tension to the picture. It is a razor-edge balance, and that balance helps shape what we can observe from far away. When scientists reconstruct black hole images, they are often interpreting light that has taken surprisingly winding journeys, guided by gravity into paths that feel almost impossible. The event horizon is not a surface. It is a point of no return. It is tempting to imagine a black hole as a dark ball with a boundary you could touch. The event horizon is not like that. It is a location in spacetime where escape to the outside universe becomes impossible. Cross it and the paths that lead outward no longer exist. For a distant observer, processes near the horizon can appear slowed and reddened because signals struggle to climb out. For someone falling in, nothing special has to happen at the boundary itself, depending on the size of the black hole. There is no sudden wall of force. The horizon is defined not by material, but by causality. It is a one-way threshold for events. That is why it is called an event horizon. Beyond it, what happens cannot influence the outside world again. This is one of the most unsettling ideas in physics because it turns a region of space into a boundary of knowledge. It tells you that the universe contains places where information can be sealed away by geometry itself. Hawking radiation suggests black holes can slowly evaporate through quantum effects. A black hole seems like the ultimate trap, yet quantum theory adds a surprising twist. Stephen Hawking showed that when you consider quantum fields near the horizon, black holes are expected to emit a faint glow. Over incredibly long times, that emission would carry energy away, and the black hole would lose mass. The effect is unimaginably weak for large black holes, so it is not something we watch happening in real time. Still, the implication is profound. It connects gravity, quantum mechanics, and thermodynamics in a way that suggests black holes have temperature and entropy. It also raises deep questions about what happens to information. If a black hole can shrink and eventually vanish, what becomes of the detailed history of everything that fell in? This is not just a detail. It is a doorway to one of the biggest puzzles in modern physics. Hawking radiation turns black holes from eternal prisons into objects with lifetimes, and it forces us to rethink what nothing escapes really means when quantum reality is allowed to speak. Gravitational wave detectors measure distortion smaller than an atomic nucleus. To detect gravitational waves, scientists build instruments that can sense a change in distance that is almost beyond imagination. Interferometers use long arms and laser light to compare travel times with extraordinary precision. When a gravitational wave passes, space itself stretches and squeezes by a tiny fraction. The detector does not shake because something hits it. It responds because the geometry between its mirrors changes. The challenge is that almost everything else can mimic that change. Trucks rumble, oceans surge, and even distant earthquakes can add noise. So the detectors are isolated, calibrated, and monitored with obsessive care. When a clear signal arrives, it carries a story from far away, often from the final moments of dense objects spiraling together. The beauty is that this is not seeing with light. It is sensing with distance. It is turning spacetime into a medium that can ring, and turning human engineering into an ear sensitive enough to hear it. That sensitivity is a triumph of patience and ingenuity, and it opens a new window on the universe. Two black holes merging can briefly outshine all stars in gravitational power. During a black hole merger, the most luminous output is not light. It is energy carried away by gravitational waves. For a brief moment, the rate at which energy is radiated can be enormous, surpassing the combined light output of all the stars in the observable universe. Yet the drama is hidden from ordinary sight because the waves interact so weakly with matter that they pass through almost everything. What reaches Earth is a gentle stretching and squeezing, like a cosmic whisper. That contrast is part of the wonder. The most powerful events can be the least flashy to the eye. The waves also carry a clean fingerprint of the system, revealing masses and spins through the changing frequency and amplitude of the signal. This is why these detections feel like listening to a story told by the universe itself. A merger is not just a collision. It is a transformation of space-time geometry, releasing energy in a form that bypasses dust, gas, and darkness. Gravity becomes the messenger, and the message is astonishingly energetic. Gravity might have a quantum carrier, but no one has seen it yet. The other forces have quantum descriptions, and their influences are carried by particles. Gravity resists that neat picture. We can describe it with extraordinary success on large scales, yet a complete quantum account remains elusive. Physicists often refer to a hypothetical carrier called the graviton, a quantum of gravitational influence, but it has not been observed. The difficulty is not only conceptual. Gravity is so weak compared to other forces that detecting a single quantum interaction would be unimaginably hard with current methods. Yet the search is not optional, because situations exist where both gravity and quantum effects matter. like the earliest moments after the Big Bang and the deep interiors of black holes. A full theory would explain how spacetime itself behaves when it must obey quantum rules. That could reveal new phenomena and resolve long-standing paradoxes. The fascination is that gravity, the force that feels most familiar, may be hiding the most radical physics. The ground under you might be the clue to a deeper layer of reality that we have not yet learned to measure. Understanding gravity better could rewrite cosmology and reveal what fills the universe. Cosmology is a story told with gravity. It is how we infer the mass of galaxies, the growth of large-scale structure, and the expansion history of the universe. Yet, major mysteries remain, including the nature of dark matter and the cause of the universe's accelerated expansion. These puzzles could mean new ingredients, or they could mean we do not fully understand how gravity behaves across enormous distances and times. Better measurements, from gravitational waves to precision surveys of galaxies, keep testing the rules. Each test is a chance for surprise. A small mismatch might point to new particles, new fields, or new geometry. This is why gravity research feels so high stakes. It is not only about explaining falling. It is about explaining the contents and fate of the cosmos. If gravity's story changes, our picture of the universe changes with it. The most familiar force could be the key to the most unfamiliar answers. As we come to the end of our journey through gravity, notice how much of life it quietly holds together. We began with the idea that gravity is not a simple tug, but a shaping of space-time itself. Then we followed that shaping outward, from the ground beneath your feet to the moon's steady orbit, and on to tides that breathe in and out along Earth's edges. We wandered through the solar system's hidden rules, where planets keep their distance by speed, and where moons can be warned from within by repeated stretching. We listened for the universe's deepest tremors, those ripples in space-time that carry news of collisions too far and too dark for ordinary light. Along the way, gravity became more than the reason things fall. It became a storyteller. It writes mountains and rivers into the land. It sets the pace of clocks. It gathers stars into galaxies and threads galaxies into a vast web. Now, you do not need to hold any of it tightly. Let it drift like starlight behind your eyelids. Feel the steady support beneath you, reliable and unhurried. Let your jaw loosen. Let your shoulders soften. Allow your breathing to find an easy rhythm, in and out, with nothing to solve and nowhere to go. If you enjoyed this journey, you might like, subscribe, or leave a quiet comment. It helps the channel reach others who could use a peaceful place to land. And if you are still awake, there should be another video waiting for you on screen, ready to carry you onward. For now, let the day fall away. Let your thoughts slow like a leaf settling to the ground. Sleep well, and good night.